Don't worry. All right. So we have a couple lessons left in this unit. So far, we've kind of done a little section on rational equations and inequalities. Then we talked about rates of change. This is kind of an extension of instantaneous rates of change. And what the nice thing is about the what we call the Newton Quotient is it allows our instantaneous rate of change methods to be less estimated. So with this method, we can actually kind of figure out exactly what an instantaneous rate of change is, whereas the methods that I kind of showed you yesterday help our understanding of this concept, but all of those are still estimated methods. So we talked about drawing the tangent line. That one is a very estimated method. We talked about choosing kind of an interval surrounding our point to create like a really small secant that's hopefully close to the slope of our tangent. And then we talked about this idea of a limit chart. And this limit chart shrinks the interval closer and closer and closer together, and then we see what the slopes of the secants are approaching. And that actually is going to help us understand what we're going to do today. Okay, so average rates of change, we talked about, they are delta y over delta x, and we do y2 minus y1, or in function notation, f at x2 minus f at x1, which is essentially just y2 and y1, over x2 minus x1. And then we talked about instantaneous rate of change at a certain x value. We sometimes use average rates of change to estimate that. So what we talked about in that little secant chart is this idea of the limit. So as we make the x's closer and closer and closer together, the change in the x's is approaching 0. So that's kind of the idea of what we're going to build on today. But this idea of the limit of the slopes of the secants is kind of what we want to explore a little bit more. Okay, so, and this says that the interval between the x's is approaching 0, so it's getting smaller and smaller and smaller. Okay, so in our charts from yesterday, we said that the instantaneous rate of change can be estimated if we look at the trend in that fourth column, where we figure out the slopes of the secants as the x's get closer and closer and closer together. Okay, and this whole idea is where the slopes of our secants or where our Newton quotient kind of comes from. So we kind of look at slopes of secants between 2 points that are getting closer and closer and closer together infinitely, technically. Okay, so an example. I have some sort of function, okay? And let's just say that I have some point x right here. Right, so this is going to be some x coordinate. The y of that point is f at x. Okay, and then I have some other point. And that some other point, let's say maybe it's up here, has some x coordinate as well, and it has some y coordinate. And we're going to say that these 2 points are some number of units away horizontally from one another. So if I measure this little like horizontal distance between these 2 points, we're going to say that these 2 points are h units apart. So if these 2 points are h units apart, what is this point? This guy right here. What's the x coordinate if this is x and I'm h units from this point here? Close. H plus x, yeah. H plus or x plus this h number of units should give me this point. Agreed? All right. So that must make the y-coordinate of this f at x plus h, right? Just the function evaluated at this x value. All right, so if I try to figure out the instantaneous rate of change for any x coordinate, the idea is that I will shrink the interval in between my 2 points. So eventually, these points actually get closer and closer and closer together, right? So that eventually the secant line approaches the slope of the tangent line, right? We talked about bringing that point closer and closer and closer together to a certain x value. That's really what we were doing in these charts up here. So if we look at our charts again, I had some x value that I was trying to find instantaneous rate of change at. It was x equals 2. And I was taking 2 points and bringing the distance between them closer and closer and closer together. So eventually we got to a difference between the x's of 0.001, right? So the closer we bring them together, the closer our slope of our secant approaches the actual slope of the tangent. That's the idea. So if we flip back over to what we have here, I want to bring these points so close together that eventually the slope of the secant that connects them is approaching the slope of the tangent line at this point, right? That's kind of the thought. So I'm just going to get rid of these because it's a little bit, I want us to be able to see what's going on here. So if I'm trying to find dy over dx, so the instantaneous rate of change at some certain x value, I normally will kind of like try to use an average rate of change over a certain interval, right? So we'll try to do like y2 minus y1 over x2 minus x1. And in our case, y2 is, let's say, f at x plus h. And our y1 is like f at x, right? And in this case, that would mean our x2 is x plus h. And our x1 is like x. So you'll notice that the x's here actually cancel out. So we're left with f at x plus h minus f at x all over h. That's not quite enough. That's not quite where I'm getting to here. I'm interested in dy over dx, or instantaneous rate of change, as the interval between x and x plus h, or the h value, goes closer and closer and closer to 0. So I want to move these points so close together, right? I want to move them like so that they're like right next to each other, so close together that this little secant in between here approaches the slope of the tangent line at that point. So here's the idea. We say that we can figure out dy over dx if we take the limit as h approaches 0. So the distance between these 2 points gets smaller and smaller and smaller and smaller until those points are super close together. And then I figure out what the slope of that secant line is. Basically exactly what we did in that limit chart from yesterday. Okay, and this is what we call Newton's quotient, or the Newton quotient. And this is basically the foundation for all of calculus. Okay, if none of that made sense to you, that's totally okay. We could still use the Newton quotient to figure out instantaneous rates of change. Basically what this will also give me, which is kind of cool, is I can actually figure out with this equation here, I can figure out the slope or the instantaneous rate of change or slope of the tangent at any point along the function that I want once I figure this out. So in our limit chart that we did from yesterday, okay, sorry, I'm trying to scroll up here and it's not working. Oh, I think we're oh, no. Come on. Sorry, I can't scroll. Give me 1 second here, let's pause this. So with our limit chart from yesterday, all I was able to do with this limit chart is estimate instantaneous rate of change when x equals 2, right? Because I was bringing the interval closer and closer and closer between 2 and some number that's super close to 2, right? This Newton quotient, if I want to estimate instantaneous rate of change at a variety of points around my function, I can actually figure this equation out and then I can sub in a variety of x values and actually find the slope of the tangent at any point that I want. So that's also the nice thing about this method is that if I wanted to find instantaneous rate of change at 2, 3, 4, and 5, I don't have to do like 4 different limit charts in order to figure that out. I just have to calculate this and then I'll plug in x equals 2, x equals 3, 4, and 5. Okay, so here's our Newton quotient. This is also called derivative from first principles. So has anyone ever heard the word derivative before? In terms of math? You've heard some other grade 12s or some grade 12 students this semester, or was it last year? This semester, yes. So there's some people learning about, or I guess they've already learned about derivatives, but that's basically all of calculus. In high school, we learn how to calculate this idea of derivatives, which are equations for instantaneous rate of change anywhere on our function. That's the idea. Okay, so I'm going to show you guys some basic examples of how we can use the Newton quotient to find instantaneous rate of change. What I like to do before I use Newton quotient, because I know that Newton's quotient asks me to input in f at x plus h, I like to, before I sub into this equation, I like to actually find out what f at x plus h is in terms of my function that I'm given. So let me ask you guys this. If I were to ask you to evaluate f at 2 for this function, what would you do? How do you calculate that? You sub it in for the x's in here, right? So what if I ask you to find f at x plus h for this function? What do I do with x plus h? Simran? We sub it in for the x's, right? So wherever I see an x, I'm replacing it with x plus h. Okay? Just like if I want to calculate f at 2, I sub in wherever I see an x, I plug in 2. Okay, now I just want to expand and simplify this guy. So we're going to do x plus h times x plus h. Remember, x plus h squared is that expression foiled out, not x squared plus h squared. I'm going to bring the 5 in here, or the negative 5, I should say. And we're just going to FOIL this expression out here. All right. You can do this inside of the Newton quotient equation, but it gets a little bit messy. So I just like to do it first off to the side, and then I'll plug that final thing into my Newton quotient. Okay, so we are going to plug in f at x plus h. Which is this whole expression right here. And then I'm going to subtract f at x. So f at x is given to us in the equation, or in the question, I should say. And I'm just going to distribute this negative into each term of f at x for that second part there.
Is that 2xh or 2 times h?
2xh. If I were saying 2 times h, I would just say 2h. Okay, and because I'm calculating dy over dx when x equals 2, I can also sub in x equals 2 for all of the x's that I have here. But you might notice first that some of these things are actually canceling out. Like I have a positive x squared and a negative x squared. I have a negative 5x and a positive 5x, and I have a positive 4 and a negative 4. Okay, so before we plug that in, actually, yeah, we're not going to plug it in just yet. Sometimes people will plug in the value first, but I like to wait until the end because then we can use it for any equation. Now, eventually, we have to do something with this in order to go further with this and figure out what that equation is for instantaneous rate of change. Jeremy? Yes, so eventually we have to do something with this, but we must write it until we actually apply it into this equation. So the limit, what's that?
It's actually part of the equation?
Yes, it's part of the equation. What we're saying is this h value is getting closer and closer and closer to 0, right? Like on our little limit charts that we did yesterday, the x's were getting closer and closer and closer together. So that's what we're saying here. How we calculate these limits is eventually we'll actually take the value that the limit is approaching and potentially sub it in here. But if we try to sub in, here's what happens. We get, right, we get 0 over 0. This is something that when we're working with limits, we call indeterminate form. And a lot of times indeterminate form simply means that we must do something else to calculate this limit, or we might need to play around a little bit so that we can get this equation a little bit more simplified before we actually evaluate this part of our equation, which is the limit part. So a lot of times what we can do, yeah, Jonathan? Yep. A lot of times what we can do is actually just common factor. And notice now that I can actually cancel out these h's if I common factor an h from the top. And what that allows us to do is it actually allows us to be able to plug in h equals 0 without getting indeterminate form. And once I plug in h equals 0, I get to drop this limit notation. So here we will get 2x plus 0 minus 5. And this actually gives us dy over dx for any x value we want on our function. Now we were asked to find the instantaneous rate of change or estimate, or not estimate I guess, or find instantaneous rate of change when x equals 3. So I can actually evaluate dy over dx when x equals 3 now by just subbing in 3 in for this equation. So it will be 1. If this equation is representing distance at time, or what time at distance, or I guess it would be distance at a certain time. It could be meters per second, kilometers per hour, that kind of idea. But our slope of our tangent at this point, x equals 3, is slope of 1. Okay, and a lot of times instead of writing out instantaneous rate of change, we'll just say like IROC, IROC. So if you see me write IROC or AROC, that means instantaneous rate of change or average rate of change.
What does the lim h to o stand for? Or h to the
So this is saying that the distance between our x's, our two x points, is getting closer and closer and closer together. So here's the idea, back to what we talked about yesterday. See how my distance between my x's is getting closer and closer and closer together? So the distance that those x's are apart is approaching 0, agreed? If I keep bringing them closer and closer and closer together. So that's that limit part in our Newton quotient, saying we want to calculate the slopes of the secants as the x's get closer and closer and closer together. Okay, this equation that we found right here will allow us to find slope of the tangent or instantaneous rate of change at any x value for f at x. Okay, so now that I have this equation, I can find instantaneous rate of change for any x value I want, just doing a really quick calculation at the end. This equation right here, often we refer to this in this notation. It looks like f with a little apostrophe, and we read this f prime at x or f prime of x. And essentially this is the notation for the derivative of the function. So this reads okay, so when I find the derivative of a function, I am finding the equation that gives me instantaneous rate of change or the slope of the tangent line at any point along a function that I could ever want to find. Okay, we're going to try another one. So actually, it's written for you here. The derivative we're going to write as f prime at x, and we're going to find that general equation for instantaneous rate of change to find the slope of the tangent at any point throughout the domain of our function. So here's our f at x function. We're going to just first find a general formula that allows us to find instantaneous rate of change anywhere. That's all it asks right here. And then it's asking us to apply our formula to find instantaneous rate of change at two different x values. Okay, so first, before we plug into our Newton quotient, I'm going to have to find f at x plus h for this function here, which means that wherever I see an x in our function above, I'm going to replace it with f at x plus h. Okay, we expanded this in the last question, so I'm just going to write what its expansion is here. And then we're going to distribute the -2 in for each term. Okay, so there is f at x plus h, all expanded out and simplified. So when you're using Newton's quotient, you must write this limit part of the equation. This is actually part of the equation. Eventually we have to sub in h equals 0. You must write it on every line until you've actually subbed in 0 for h. You usually can't do that at the beginning because you have to do some math work like maybe common factoring or simplifying before you're able to do that. Okay, we don't want to get indeterminate form. So we're going to enter in f at x plus h, which we just calculated above. And we're going to subtract f at x. Okay, and usually what you're going to notice at this step is that a couple things will cancel out. What do you guys notice is canceling out here? Alexandra?
The negative 2x squared and the plus 2x squared.
Yep, anything else? Liam? 7 and negative 7. Okay, so here's what we've got left at this point. Great, so if I enter in h equals 0 at this point, we're going to get indeterminate form. So what we're going to have to do here is we're going to have to first common factor an h out from the top. And now I'm going to be able to cancel out an h from the top and bottom. And then I'm going to actually evaluate this limit part of the function by subbing in h equals 0. Okay, at this point, we can drop the limit notation. Okay, because now we've taken care of that calculation.
Does that say not allowed?
What?
It drops the limit on-
Notation.
Oh.
Sorry, one word. There you go. Now it looks like it connects. Okay, so here we just found f prime at x, or the derivative of f at x, which gives me slope of the tangent at any x value I could ever want, or instantaneous rate of change at any x value I could ever want. This is the general equation for the slope of my tangent, or instantaneous rate of change. It's negative 4x. Now this asks me to use f prime at x from above to find instantaneous rate of change at x equals 1 and x equals negative 3. So I'm going to evaluate f prime at 1, which gives me negative 4. So the slope of my tangent line when x equals 1 is negative 4. And I'm going to evaluate f prime at negative 3. And I'll get 12. So the slope of my tangent line when x equals negative 3 is 12. Or instantaneous rate of change is 12.
What's all that just for negative 4x?
See, this is why we need calculus, right? Because this whole thing is pretty tedious, especially to do for like every single different type of function. So calculus allows us basically to go from this right to this.
So why aren't we learning that right now?
Because you're not in calculus. That would be the first reason why.
You go down.
What?
Is like doing that process in calculus easier than this one?
Yeah, but there's a bunch of, so the whole calculus course is basically like you learn all the different rules for how you can find these things, and it's different for different types of functions. So that's why you kind of need the whole course in order to do it.
So we're like learning the basics.
So you guys are learning why calculus works basically right now. All right, so I'm going to ask you guys to try out some of these questions from the worksheet here, see what you can do with them, and yeah, see if you can use Newton Quotient. You might even be able to see a pattern as you start to find some derivatives, especially of these questions in part 1, at least A, B, C, D. You might be able to see a pattern of how you can actually use calculus to figure these out.